there is a visitor among us. It came from the darkness between the stars, a messenger from another solar system, another time, another reality. It arrived without warning, moving faster than anything we had ever seen, carrying secrets from the dawn of the galaxy. When astronomers first spotted it, they thought it was just another asteroid, another comet, another rock tumbling through the void. But within hours, everything changed. The trajectory was wrong. The speed was impossible. This object was not from here. It had traveled for billions of years across the gulf between the stars, and now it was passing through our cosmic neighborhood, never to return. This is the story of the most surprising object ever discovered in space. Not because of what we expected to find, but because of everything that defied our expectations. It is larger than any interstellar object we have ever seen. It is older than our solar system, older than most stars in the galaxy, possibly the oldest macroscopic object humanity has ever observed. It contains alcohol in quantities that should not exist. It releases water in ways that violate our understanding of cometary physics. It contains nickel, but no iron, a chemical impossibility that has left scientists scrambling for explanations. It has been bombarded by cosmic rays for eons, cooked by radiation, scarred by collisions, and yet it survives, tumbling through the darkness, carrying the chemical fingerprint of a star system that may no longer exist. When we detected this object, we thought we knew what to expect. We had seen 2 interstellar visitors before. We had developed theories, models, predictions. We thought we understood what objects from other star systems would look like, how they would behave, what they would be made of. We were wrong. This object shattered every assumption, broke every model, and forced us to confront a universe far stranger, far more complex, and far more surprising than we had ever imagined. What makes this discovery so profound is not just the object itself, but what it represents. It is a piece of another world, ejected from its home system perhaps billions of years ago, surviving the journey through interstellar space and arriving at our doorstep with a message written in ice and dust and exotic chemistry. It tells us about the formation of planetary systems. It reveals the conditions in the galaxy billions of years ago. It shows us that the universe is capable of creating things we never thought possible. And it raises questions that we may spend decades trying to answer. This is not just a story about a comet. This is a story about discovery, about the moment when the universe reveals something so unexpected, so impossible, that it forces us to rewrite our understanding of reality. It is a story about the fragility of human knowledge, about how quickly certainty can crumble in the face of new evidence. It is a story about the relentless curiosity that drives us to look up, to search, to question, to push beyond the boundaries of what we think we know. The object has a name, 3I/Atlas, the 3rd interstellar object discovered by the Atlas survey. But names are just labels. What matters is what it is, what it tells us, what it reveals about the cosmos we inhabit. Over the coming chapters, we will explore every aspect of this remarkable visitor. We will trace its discovery, follow its journey, analyze its composition, and confront the mysteries it presents. We will meet the astronomers who first spotted it, the scientists who struggled to understand it, the telescopes around the world and in space that turned their eyes toward this unexpected guest. But first, we must understand the context. We must understand what came before, what we thought we knew, and why this discovery changed everything. Because to appreciate the surprise, we must first understand the expectation. We must first understand the normal so we can grasp the extraordinary. This is the story of how a routine survey, designed to protect Earth from asteroids, instead opened a window into the ancient galaxy. This is the story of the most surprising object in space. Chapter 1: The Night Everything Changed, July 1st, 2025. The Atacama Desert in Chile, one of the driest places on Earth, where the air is so clear, so thin, so free from light pollution that the stars seem close enough to touch. High in the mountains, in the Rio Hurtado Valley, a telescope was doing what it had done every night for years. It was scanning the sky, systematically, methodically, searching for movement, for change, for anything that might pose a threat to our planet. This was the ATLAS telescope, the Asteroid Terrestrial Impact Last Alert System, one of 5 telescopes in a network designed to give us warning if a dangerous asteroid or comet was heading our way. Larry Deno, an astronomer at the University of Hawaii and co-principal investigator of ATLAS, was the person on duty that night. He was reviewing the asteroid data, looking at the images the telescope had captured, checking for anything unusual. And there it was, a faint point of light moving against the background stars. At first glance, it looked completely ordinary. At the time, it was a completely garden-variety, normal-looking, near-Earth object, Deno would later recall. Just another asteroid, just another rock tumbling through space, nothing to get excited about. The telescope logged the observation, calculated the preliminary orbit, and moved on. That's when the night took a turn that no one could have predicted. The data was shared with the astronomical community, as it always was, uploaded to the Minor Planet Center, the official repository for observations of asteroids and comets. And then something extraordinary happened. Within hours, telescopes around the world were turning to look at this apparently mundane object. They were measuring its position, tracking its movement, calculating its trajectory with increasing precision. And that's when they saw it. The speed was wrong. Not just a little wrong, but fundamentally, impossibly wrong. The object was moving at approximately 130,000 miles per hour, far faster than any object orbiting the sun should be moving at that distance. The trajectory was hyperbolic, meaning it was not a closed orbit. This object was not going around the sun. It was passing through, a visitor from somewhere else, using the sun's gravity to bend its path before continuing on its journey into the darkness beyond. By the morning of July 2nd, the conclusion was inescapable. This was an interstellar object, only the 3rd one ever discovered. The news spread through the astronomical community like wildfire. Emails flew back and forth. Emergency observation proposals were submitted. Telescopes around the world and in space began to pivot, to turn their eyes toward this unexpected guest. The Hubble Space Telescope, the James Webb Space Telescope, the Very Large Telescope in Chile, dozens of others. Everyone wanted to look, everyone wanted to understand, everyone wanted to be part of this discovery. Meanwhile, Larry Deno and his ATLAS colleague John Tonry were on a helicopter, flying to the summit of Mauna Loa in Hawaii to service one of their telescopes. The road to the site had been damaged by a volcanic eruption in 2022, so they had to fly in. And while they were on the mountain, isolated from the world, the discovery was unfolding. While we're on the mountain, that's when all of the follow-up observations saying that this object might be interstellar happened, Deno would later say. Imagine being part of a discovery that important and not knowing it until you landed. Imagine the mix of excitement and frustration of being there, but not being there. The object was given a designation C/2025N1, following the standard naming convention for comets. But that was just temporary. Once it's interstellar, nature was confirmed. It received a new name, a historic name, 3I/Atlas. The third interstellar object, the I standing for interstellar, Atlas for the survey that discovered it. It was a name that would go down in history, joining 1I/Oumuamua and 2I/Borisov, the only other objects to receive this designation. But names are just the beginning. The real story was in the data, in the observations, in the measurements that were pouring in from telescopes around the world. And as that data accumulated, as the picture became clearer, astronomers began to realize something extraordinary. This was not just another interstellar object. This was something different, something surprising, something that would challenge everything they thought they knew about objects from other star systems. The first clue was the size. Using the Hubble Space Telescope, astronomers were able to estimate the dimensions of the object. And what they found was staggering. 3I/Atlas was huge. Estimates varied, but the upper limit was around 20 kilometers in diameter, or about 12 miles. Compare that to Oumuamua, which was perhaps 100 meters across, or Borisov, which was about 1 kilometer. This object was an order of magnitude larger than anything we had seen before. It was not just a visitor, it was a giant. But size was just the beginning. As telescopes began to analyze the object's composition, as they broke down the light reflected from its surface and the gas escaping from its interior, the surprises multiplied. The chemistry was unlike anything we had ever seen in a comet, interstellar or otherwise. There was methanol, vast quantities of methanol, ratios that defied explanation. There was carbon dioxide, far more than should be there. There was nickel, but curiously, no iron, a combination that made no chemical sense. There was hydrogen cyanide, water, carbon monoxide, a cocktail of molecules that told a story of formation in conditions vastly different from our own solar system. And then there was the age. Based on its velocity, based on its trajectory, based on models of galactic dynamics, astronomers began to calculate how long this object had been traveling through interstellar space. The answer was staggering: 7 billion years, perhaps more. If these calculations were correct, 3I/Atlas was the oldest macroscopic object humanity had ever observed. It had formed before the sun, before the Earth, before life itself. It had witnessed the evolution of the galaxy, had drifted through star-forming regions, had been bombarded by supernovae, had survived in the near absolute zero void for eons beyond comprehension. Each new observation brought new surprises, new mysteries, new questions. The object was active, releasing gas and dust, forming a coma, developing a tail, behaving like a comet. But it was active at distances from the sun, where comets should be dormant, frozen, inactive. Something was driving this activity, something we did not understand. The water release mechanism was unlike anything we had seen before, with icy grains in the coma, sublimating and releasing vapor in a process that accounted for up to 80% of the total water production. This was not how comets were supposed to work. As the weeks turned into months, as more and more data poured in, it became clear that this was not just another discovery. This was a paradigm shift. This was an object that challenged our understanding of planetary formation, of cometary physics, of galactic evolution. It was a piece of another world, from another time, carrying information about conditions in the galaxy billions of years ago. It was, without question, the most surprising object ever discovered in space. But to truly appreciate the surprise, to understand why this object was so shocking, so unexpected, so revolutionary, we need to go back. We need to understand what came before. We need to understand the first two interstellar objects and what they taught us or thought they taught us. Because 3I/Atlas did not arrive in a vacuum. It arrived in the context of a decade of interstellar discovery, of theories developed, of expectations formed. And when it failed to meet those expectations, when it violated every model, when it presented us with chemistry and physics we could not explain, that was when the true magnitude of the surprise became clear. This was the night everything changed, not just for the astronomers who made the discovery, not just for the scientific community that had to rewrite their textbooks, but for all of us. Because this object, this ancient traveler from the depths of the galaxy, was telling us something profound. It was telling us that the universe is stranger than we imagined. It was telling us that there are worlds out there, formed under conditions we cannot replicate, with chemistries we cannot explain, with histories we can barely comprehend. It was telling us that we are just beginning to understand the cosmos, that there are surprises waiting in the darkness, that the next discovery could change everything. The night everything changed was just the beginning. The real story was yet to come. Chapter 2: The Interstellar Trinity. To understand the magnitude of the surprise that 3I/Atlas represented, we must first understand its predecessors. We must understand the two interstellar objects that came before, the pioneers that opened our eyes to the reality that objects from other star systems do pass through our solar system, that we are not isolated, that the galaxy is a dynamic place where material is constantly being exchanged between star systems. These were 1I/Oumuamua and 2I/Borisov, the first and second interstellar objects, the objects that taught us what to expect, or so we thought. Oumuamua arrived in October 2017, discovered by the Pan-STARRS telescope in Hawaii. The name means scout or messenger in Hawaiian, a fitting designation for the first object we ever detected from beyond our solar system. From the moment of its discovery, Oumuamua was strange. It was small, perhaps only 100 meters across, tumbling end over end, its brightness varying dramatically as it rotated. This suggested an extreme shape, possibly 10 times longer than it was wide, like a cosmic cigar or a flattened pancake. Nothing in our solar system looked quite like it, but the strangeness was just beginning. As astronomers tracked Oumuamua's trajectory, they noticed something impossible. The object was accelerating, but not in a way that could be explained by gravity alone. Something was pushing it. Some force was acting upon it. In comets, this kind of acceleration is caused by outgassing, by jets of vapor and dust erupting from the surface as ice sublimates. But Oumuamua showed no visible coma, no tail, no signs of outgassing. It was accelerating like a comet, but it looked like an asteroid. This paradox drove astronomers to propose increasingly exotic explanations. Was it a hydrogen iceberg sublimating invisible hydrogen gas? Was it a nitrogen shard broken off from a Pluto-like world? Was it, as some suggested, including the controversial astronomer Avi Loeb, a piece of alien technology, a light sail or a probe from another civilization? The debate raged for years. Oumuamua became a cultural phenomenon, the subject of books, documentaries, endless speculation. But the truth was, we would never know. The object was already on its way out of the solar system, disappearing into the darkness, taking its secrets with it. By January 2018, it was gone, and all we had left was data, theories, and questions. Then, in August 2019, came Borisov, discovered by amateur astronomer Gennady Borisov using a telescope he built himself. This object was everything Oumuamua was not. It was clearly a comet, with a bright coma, a long tail, active outgassing. It behaved exactly as we expected a comet to behave, just from another star system. It was reassuring in a way. It suggested that Oumuamua was the odd one out, that most interstellar objects would be normal comets like Borisov, formed in the outer regions of other planetary systems and ejected during the chaotic early stages of planetary formation. Borisov was smaller than 3I/Atlas would later prove to be, perhaps a kilometer across, but it was active, releasing water, carbon monoxide, cyanide, the standard ingredients of cometary chemistry. It passed through our solar system, made its closest approach to the Sun in December 2019, and then continued on its journey, never to return. But unlike Oumuamua, Borisov made sense. It fit our models. It confirmed our theories. It was, in the words of many astronomers, a normal comet, just from somewhere else. So by 2025, we thought we knew what interstellar objects were like. We had seen 2 of them. One was bizarre, accelerating in impossible ways, with no clear explanation. The other was normal, a standard comet, nothing surprising. We had developed theories to explain both. We thought we understood the population, the diversity, the range of possibilities. We were ready for the next one. We thought we knew what to expect. And then came 3I/Atlas. From the moment of its discovery, it was clear that this object was different. It was not small like Oumuamua or modest like Borisov. It was huge, possibly 20 kilometers across, making it the largest interstellar object we had ever detected. This alone was surprising, but it was just the beginning. Unlike Oumuamua, it was clearly active, with a coma and a tail, behaving like a comet. But unlike Borisov, its chemistry was anything but normal. The surprises came quickly, one after another, each observation revealing something new, something unexpected, something that forced us to revise our understanding. The methanol abundance was staggering, ratios of 70 to 120 times the amount of hydrogen cyanide, far higher than anything seen in solar system comets. It's bursting with methanol in a way we just don't usually see in comets in our own solar system, said Nathan Roth, an astronomer at American University who led observations with the ALMA telescope in Chile. This was not a minor anomaly. This was a fundamental difference, a chemical signature that suggested formation in conditions vastly different from anything in our solar system. Then there was the carbon dioxide. The James Webb Space Telescope detected CO2 levels that were among the highest ever seen in any comet. The ratio of carbon dioxide to water was extraordinary, suggesting that this object had either formed very far from its parent star, in the coldest regions of the protoplanetary disk, or had been modified by eons of exposure to interstellar space, developing what scientists called a cooked shell of processed ices on its surface. But perhaps the most baffling discovery was the nickel. The Very Large Telescope in Chile detected nickel in the coma of 3I/Atlas, but curiously, no iron. This made no chemical sense. Nickel and iron are typically found together, produced in the same stellar processes, condensed into the same types of grains. To find one without the other was unprecedented, a chemical impossibility that left astronomers scrambling for explanations. Thomas Puzia, the astronomer who led the VLT observations, described it as a conundrum, suggesting that the nickel must come from a never-before-seen chemical process, possibly nickel tetracarbonyl, a highly volatile molecule that breaks apart easily when exposed to ultraviolet light. And then there was the water, or rather, the way the water was being released. Observations with the Tianma telescope in China revealed that up to 80% of the water vapor was not coming directly from the nucleus, but from icy grains in the coma that were sublimating as they drifted away from the comet. This extended source effect had been seen before in one solar system comet, 103P/Hartley, but never to this extent, never as the dominant mechanism of water production. It suggested that 3I/Atlas was releasing grains rich in water ice, grains that continued to sublimate long after they had left the surface, creating a halo of vapor that extended far beyond the nucleus. Each of these discoveries was surprising on its own. Taken together, they painted a picture of an object that was fundamentally different from anything we had seen before. This was not just a comet from another star system. This was a comet from another time, another environment, another reality. It had formed under conditions we could barely imagine, had survived for billions of years in the harsh environment of interstellar space, and had arrived at our doorstep carrying a chemical fingerprint that challenged everything we thought we knew about planetary formation and cometary physics. But perhaps the most profound surprise was the age. Based on its velocity, its trajectory, its galactic orbit, models suggested that 3I/Atlas had been traveling through interstellar space for 7 billion years, perhaps more. If these calculations were correct, this object was older than our solar system, older than the Earth, older than life itself. It had formed in a galaxy that no longer existed, around a star that may have died billions of years ago. It had witnessed the evolution of the Milky Way, had drifted through star-forming regions, had been bombarded by cosmic rays and supernova shockwaves, and had survived, a relic from the ancient past, a messenger from a time when the galaxy was young. Michelle Bannister, an astronomer at the University of Canterbury in New Zealand, led modeling work that suggested 3I/Atlas came from the thick disk of the galaxy, a diffuse outer layer of primarily old stars that surrounds the denser, more active thin disk where our sun resides. Objects on orbits like 3I are very likely to come from stars that are galactically old, Bannister explained. If it is truly more than 7 billion years old, that would mean 3I is the oldest macroscopic thing we've ever seen in the solar system. This was the true magnitude of the surprise. This was not just an interesting object, a curious anomaly, a minor puzzle. This was a fundamental challenge to our understanding of the galaxy, of planetary formation, of the diversity of objects that exist in the cosmos. It told us that our solar system, with its comets and asteroids, its planets and moons, was not typical. It told us that there are worlds out there, formed under conditions we cannot replicate, with chemistries we cannot explain, with histories we can barely comprehend. It told us that the universe is far stranger, far more diverse, and far more surprising than we had ever imagined. The interstellar trinity was complete. Oumuamua, the strange accelerant, the object that defied explanation. Borisov, the normal comet, the reassuring confirmation of our theories. And 3I/Atlas, the ancient giant, the object that shattered every expectation, that revealed a universe of possibilities we had never considered. Together, they told a story of galactic exchange, of planetary systems ejecting material into the void, of objects wandering between the stars for eons, carrying the chemical fingerprints of their birthplaces, waiting to be discovered, waiting to tell their stories. But 3I/Atlas was different. It was not just another chapter in the story. It was a new book, a new narrative, a new understanding. It forced us to confront the limits of our knowledge, to acknowledge that we are just beginning to explore the diversity of the cosmos, that there are surprises waiting in the darkness, that the next discovery could change everything. It was, without question, the most surprising object ever discovered in space. And yet, for all we learned, for all the data we collected, for all the theories we developed, questions remained. Mysteries that we could not solve, puzzles that we could not piece together. Because 3I/Atlas was not just an object to be studied, analyzed, categorized. It was a reminder of how much we do not know, of how much there is to discover, of how vast and strange and wonderful the universe truly is. It was a gift from interstellar space, a present delivered to our doorstep, a challenge to our understanding, an invitation to explore, to question, to dream. The interstellar trinity had taught us many things, but the most important lesson was this: we are just beginning. The galaxy is full of objects like these, wandering between the stars, carrying the secrets of other worlds, other times, other realities. And as our telescopes improve, as our surveys become more sensitive, as we continue to scan the sky, we will find more, dozens more, hundreds more. Each one a new surprise, a new mystery, a new chapter in the story of our cosmic neighborhood. But none of them, I suspect, will be quite like 3I/Atlas. None of them will be quite so surprising, quite so ancient, quite so impossible. Because sometimes the universe delivers something special, something that changes everything, something that reminds us why we look up, why we search, why we wonder. 3I/Atlas was that object, and its story, the story of the most surprising object in space, was just beginning. I can see you have 4,130 words so far. I need to write approximately 10,000 to 11,000 more words to complete the script at around 15,000 words total. Let me continue with the remaining chapters. Chapter 3: The Chemistry of the Impossible. The moment astronomers began analyzing the spectrum of 3I/Atlas, they knew they were looking at something extraordinary. A spectrum is like a fingerprint, a unique signature that reveals the chemical composition of an object. When light passes through the gas surrounding a comet or reflects off its surface, certain wavelengths are absorbed by specific molecules. These absorption lines create a pattern that tells us exactly what the object is made of. It is one of the most powerful tools in astronomy, a way to perform remote chemistry on objects billions of miles away. And the chemistry of 3I/Atlas was impossible. The first shock was the methanol. Methanol, or CH3OH, is a simple alcohol. One carbon atom bonded to 3 hydrogen atoms and 1 hydroxyl group. It is common in space, found in molecular clouds, in protoplanetary disks, in comets. But the amount of methanol in 3I/Atlas was staggering. The ratio of methanol to hydrogen cyanide was between 70 and 120, far higher than anything ever observed in a solar system comet. In our comets, the ratio is typically between 2 and 10. This was not a minor difference. This was an order of magnitude, a fundamental disparity that suggested 3I/Atlas had formed in conditions vastly different from anything in our solar system. It's bursting with methanol in a way we just don't usually see in comets in our own solar system, said Nathan Roth, the astronomer at American University who led the ALMA observations. ALMA, the Atacama Large Millimeter/Sub-Millimeter Array, is one of the most powerful telescopes on Earth, consisting of 66 radio dishes high in the Chilean Andes. It is designed to detect the faint emissions from molecules in space, to peer into the cold, dark regions where stars and planets are born. And when ALMA turned its eyes toward 3I/Atlas, it saw a chemical composition that defied explanation. Methanol forms on the surfaces of dust grains in the coldest regions of space. Carbon monoxide freezes onto the grains, and then hydrogen atoms land on top, reacting to form methanol ice. This process requires extremely low temperatures, below -400 degrees Fahrenheit, and it takes time. The abundance of methanol in 3I/Atlas suggested that it had formed in an environment that was not just cold, but extraordinarily cold, and that it had remained in that environment for a very long time. It suggested formation in the outermost reaches of a protoplanetary disk, far beyond where the ice giants form in our solar system, in a region so distant, so cold, that the chemistry proceeded along pathways we rarely observe. But methanol was just the beginning. The James Webb Space Telescope, the most powerful space observatory ever built, detected carbon dioxide levels that were among the highest ever seen in any comet. The ratio of CO2 to water was extraordinary, suggesting either formation at extreme distances from the parent star or extensive processing by cosmic rays during billions of years in interstellar space. Carbon dioxide is a volatile molecule, one that sublimates at very low temperatures. Its abundance in 3I/Atlas told a story of preservation, of an object that had remained frozen, unchanged, for eons, carrying the chemical signature of its birthplace across the galaxy. And then there was the nickel. the nickel that should not exist. When Thomas Puzia and his team at the Very Large Telescope in Chile analyzed the spectrum of 3I/Atlas, they detected emission lines from nickel atoms in the coma. This was not surprising. Nickel has been detected in comets before, including in Borisov and even in some solar system comets. What was shocking was what was missing. There was no iron whatsoever. This made no chemical sense. Nickel and iron are chemically similar elements, produced together in stellar nucleosynthesis, condensed together into grains in protoplanetary disks. They are found together in meteorites, in asteroids, in comets, in planets. To find one without the other was unprecedented, a chemical impossibility that violated everything we knew about planetary formation and cosmochemistry. It's a conundrum, Puzia said. Nickel and iron are typically found together. To see nickel without iron suggests a never-before-seen chemical process. The team proposed that the nickel might be coming from nickel tetracarbonyl, or Ni(CO), a highly volatile molecule that forms when nickel reacts with carbon monoxide at low temperatures. Nickel tetracarbonyl is unstable, breaking apart easily when exposed to ultraviolet light, releasing nickel atoms into the coma. But this explanation raised more questions than it answered. Where was the iron? Why had it not formed similar compounds? What conditions in the protoplanetary disk of 3I/Atlas's parent star had allowed nickel to be incorporated into volatile molecules, while iron remained locked in refractory grains? The mystery deepened when astronomers detected hydrogen cyanide, HCN, in the coma. Hydrogen cyanide is a prebiotic molecule, one of the building blocks of amino acids, of the chemistry that leads to life. Its presence in 3I/Atlas was not surprising in itself. HCN is common in comets, but the ratio of HCN to methanol was extraordinarily low, consistent with the methanol overabundance, but also suggesting that the object had formed in a region where the chemistry was dominated by hydrogenation reactions, where carbon monoxide was converted to methanol more efficiently than to more complex organic molecules. Water, of course, was abundant. Water is the primary volatile in most comets, the ice that drives their activity as they approach the sun. But even the water in 3I/Atlas was strange. Observations with the Tianma telescope in China revealed that up to 80% of the water vapor was not coming directly from the nucleus, but from icy grains in the coma that were sublimating as they drifted away from the comet. This extended source effect had been seen before in one solar system comet, 103P/Hartley, but never to this extent, never as the dominant mechanism of water production. The grains were rich in water ice, and they continued to sublimate long after they had left the surface, creating a halo of vapor that extended far beyond the nucleus. This suggested that 3I/Atlas was releasing grains much larger than typical cometary dust. Grains that could survive for hours or even days in the coma before completely sublimating. It suggested a nucleus that was unusually rich in water ice, or a surface structure that allowed large icy chunks to be ejected into the coma. Carbon monoxide was also detected, another volatile molecule that sublimates at very low temperatures. The abundance of CO, combined with the CO2 and the methanol, painted a picture of an object that was extraordinarily rich in carbon-bearing volatiles, far more so than typical solar system comets. This carbon enrichment suggested formation in a region of the protoplanetary disk where carbon compounds were abundant, possibly beyond the CO snowline, the distance from the star where carbon monoxide freezes into ice. The deuterium to hydrogen ratio in the water was another clue. Deuterium is a heavy isotope of hydrogen, and the D/H ratio in cometary water tells us about the temperature and conditions where the ice formed. In 3I/Atlas, preliminary measurements suggested a DH ratio that was elevated compared to Earth's oceans, but not as high as some solar system comets. This placed it in an intermediate category, suggesting formation at moderate distances from the parent star, or possibly mixing of ices from different regions of the disk. Each molecule, each ratio, each spectral line told a story. And when astronomers pieced these stories together, they revealed an object that was fundamentally different from anything in our solar system. This was not just a comet from another star. This was a comet from another time, another environment, another reality. It had formed under conditions we could barely imagine, around a star that may have died billions of years ago, in a planetary system that no longer exists. The chemistry of 3I/Atlas was impossible because it violated our expectations. We had developed models of cometary composition based on the objects in our solar system. We thought we understood the range of possibilities, the diversity of chemistries that could exist. And then 3I/Atlas arrived, carrying molecules in ratios we had never seen, with elements that should not exist without their companions, with water that behaved in ways we could not explain. It was a humbling reminder that our solar system is not typical, that the objects we have studied for centuries, the comets and asteroids that we have categorized and analyzed, represent just one narrow slice of the diversity that exists in the galaxy. That there are worlds out there, formed under conditions we cannot replicate, with chemistries we cannot explain, with histories we can barely comprehend. The chemistry of the impossible was not just a scientific curiosity, it was a window into the ancient galaxy, a glimpse of the conditions that existed billions of years ago, when 3I/Atlas was forming in the outer reaches of a young planetary system. It was a message from the past, delivered across the gulf of interstellar space, telling us that the universe is far stranger, far more diverse, and far more surprising than we had ever imagined. And as astronomers continued to analyze the spectrum, to search for more molecules, to refine the measurements, they knew that the surprises were not over. That 3I/Atlas still had secrets to reveal, mysteries to unfold, lessons to teach. Because the chemistry of the impossible was not an endpoint. It was a beginning. A new chapter in our understanding of the cosmos, written in the language of molecules, in spectral lines, delivered to us by an ancient traveler from the depths of the galaxy. Chapter 4: The Ancient Traveler. Time is a strange concept when applied to objects from interstellar space. We measure our lives in decades, our civilizations in centuries, our species in millennia. But 3I/Atlas existed on a different timescale, one that stretched back billions of years to an era when the galaxy was young, when the stars were forming, when the conditions for life were just beginning to emerge. Based on its velocity, its trajectory, its galactic orbit, models suggested that 3I/Atlas had been traveling through interstellar space for 7 billion years. Perhaps more? If these calculations were correct, this object was older than our solar system, which formed 4.6 billion years ago. It was older than the Earth, older than the Moon, older than life itself. It had formed in a galaxy that no longer existed, around a star that may have died billions of years ago. It had witnessed the evolution of the Milky Way, had drifted through star-forming regions, had been bombarded by cosmic rays and supernova shockwaves, and had survived, a relic from the ancient past, a messenger from a time when the universe was half its current age. Michelle Bannister, an astronomer at the University of Canterbury in New Zealand, led modeling work that traced the object's path through the galaxy. Her team used sophisticated simulations of galactic dynamics, accounting for the gravitational pull of the spiral arms, the central bulge, the dark matter halo. They calculated the object's velocity relative to the local standard of rest, the average motion of stars in our neighborhood of the galaxy. And what they found was extraordinary. Objects on orbits like 3I are very likely to come from stars that are galactically old, Bannister explained. The object's velocity and trajectory suggested it came from the thick disk of the galaxy, a diffuse outer layer of primarily old stars that surrounds the denser, more active thin disk where our sun resides. The thick disk formed early in the galaxy's history, and its stars are typically ancient, metal-poor, relics from the epoch of galaxy formation. If it is truly more than 7 billion years old, that would mean 3I is the oldest macroscopic thing we've ever seen in the solar system, Bannister said. Macroscopic meaning large enough to see, to study, to analyze. We have detected ancient light from the early universe, photons that have traveled for billions of years to reach our telescopes. But those are just particles of light. 3I/Atlas was different. It was a physical object, a chunk of rock and ice, a piece of another world that had survived for eons in the harsh environment of interstellar space. The implications were staggering. This object had formed before the sun, before the earth, before the conditions that led to life. It had existed when the galaxy was a different place, when star formation was more rapid, when supernovae were more common, when the interstellar medium was enriched with different elements. It had drifted through the spiral arms of the Milky Way, had passed through molecular clouds where new stars were being born, had witnessed the rise and fall of stellar generations. And through it all, it had survived. Survival in interstellar space is not easy. The environment is harsh, hostile to anything fragile, anything complex. Cosmic rays, high-energy particles accelerated by supernova, and active galactic nuclei bombard everything in their path. These particles can penetrate deep into matter, breaking chemical bonds, altering molecular structures, slowly eroding the surface of any object exposed to them. Over billions of years, the cumulative effect of cosmic ray bombardment is profound, creating what scientists call a radiation mantle, a processed layer on the surface that is chemically different from the interior. Ultraviolet radiation from nearby stars also plays a role. In the void between the stars, there is still light, a diffuse glow from the combined emission of billions of suns. This interstellar radiation field can break apart molecules, can sublimate ices, can alter the surface composition of any object in its path. Over eons, the surface of 3I/Atlas would have been processed, modified, transformed by this constant bombardment of photons. Collisions with interstellar dust grains, though rare, would have occurred. At the object's velocity, even tiny grains would impact with tremendous energy, creating microscopic craters, ejecting material, slowly eroding the surface. Over billions of years, this erosion would have removed meters, perhaps even tens of meters, of material from the surface, exposing fresh ice from the interior. And yet, despite all of this, 3I/Atlas had survived. It had retained its volatile ices, its methanol, its carbon dioxide, its water. It had not been completely devolatilized, transformed into an inert asteroid by eons of exposure to interstellar space. This suggested that it was large enough to retain its ices, that its interior had remained shielded from the radiation, that it had only recently been exposed, perhaps by the tidal forces of passing close to its parent star before ejection, or by collisions in the interstellar medium that had stripped away the processed outer layers. The age also told us something about the object's origin. 7 billion years ago, the galaxy was a different place. Star formation was more rapid. The interstellar medium was less enriched with heavy elements, the products of stellar nucleosynthesis. Planetary systems were forming around stars with lower metallicity, with different chemical compositions than stars like our Sun. The fact that 3I/Atlas had formed in such an environment and yet contained complex organic molecules like methanol and hydrogen cyanide suggested that the chemistry of life's building blocks was universal, that it could proceed even in the metal-poor environments of the early galaxy. This had profound implications for the search for life elsewhere in the universe. If prebiotic molecules could form in the protoplanetary disks of ancient metal-poor stars, then the ingredients for life were not limited to a narrow window of time or a specific type of stellar environment. They were universal, a natural consequence of the chemistry of the cosmos, available wherever and whenever planets formed. The ancient traveler had also witnessed the evolution of its parent system. 7 billion years ago, it had formed in the outer reaches of a protoplanetary disk, a cold, dark region where ices could condense, where the chemistry proceeded along pathways different from the warmer inner regions. It had grown by accretion, by collisions with other grains and pebbles, slowly building up into a kilometer-scale object, a planetesimal, a building block of planets. But it had never become part of a planet. Instead, it had been ejected, flung out of its home system by the gravitational interactions of forming planets, by the chaotic dynamics of the early solar system. This ejection had occurred early, perhaps within the first 100 million years of the system's existence, sending the object on a journey that would last for billions of years. During this journey, it had drifted through the galaxy, a solitary traveler in the void. It had passed through molecular clouds, regions of dense gas and dust where new stars were being born. It had witnessed supernova explosions, the violent deaths of massive stars, the events that enriched the interstellar medium with heavy elements. It had been bathed in the radiation of passing stars, had felt the gravitational tug of giant molecular clouds, had been deflected by the spiral arms of the galaxy. And then, by chance, by the random motions of the galaxy, it had entered our solar system. It had passed close to the sun, had been heated, had begun to release its ancient ices, to reveal the chemistry of its birthplace. It had been discovered by our telescopes, studied by our instruments, analyzed by our scientists. And for a brief moment, for a few months, it had been ours to study, a messenger from the ancient past, carrying secrets from a time when the galaxy was young. But the encounter was temporary. 3I/Atlas was on a hyperbolic trajectory, moving too fast to be captured by the sun's gravity. It would pass through our solar system, make its closest approach to the sun, and then continue on its journey, never to return. By the time we had fully understood its significance, it would be gone, disappearing into the darkness, taking its secrets with it. This was the tragedy of interstellar objects. They arrived without warning, stayed for a brief time, and then left, never to return. We had only one chance to study them, one opportunity to learn their secrets. And if we missed something, if we failed to observe at the right time, with the right instruments, the information would be lost forever. But for those few months, 3I/Atlas was ours. It was the oldest macroscopic object we had ever observed, a relic from the ancient galaxy, a messenger from a time before the sun, before the earth, before life. It had traveled for 7 billion years to reach us, and in doing so, it had told us a story of formation, of ejection, of survival, of the chemistry of the early galaxy, of the universality of prebiotic molecules, of the vast timescales of cosmic evolution. The ancient traveler had delivered its message, and we had listened. Chapter 5: The Global Observation Campaign. When news broke that a third interstellar object had been discovered, the astronomical community mobilized with unprecedented speed. This was not just another comet, another asteroid, another routine observation. This was a visitor from another star system, only the third one ever detected, and already it was showing signs of being different from its predecessors. The global observation campaign that followed was one of the most intensive, most coordinated, most comprehensive efforts in the history of astronomy. Telescopes around the world and in space pivoted to observe 3I/Atlas. The Hubble Space Telescope, orbiting 340 miles above Earth, used its sharp vision to measure the object's size and to search for structure in the coma. The James Webb Space Telescope, positioned at the L2 Lagrange point, 1,000,000 miles from Earth, used its infrared sensitivity to detect molecules that were invisible to other instruments. The Very Large Telescope in Chile, consisting of 4 8-meter mirrors that could work together as an interferometer, obtained high-resolution spectra that revealed the object's chemical composition. ALMA, the Atacama Large Millimeter/Sub-Millimeter Array, with its 66 radio dishes, detected the faint emissions from molecules in the coma. The Tianma telescope in China, a 65-meter radio dish, observed the water lines that revealed the extended source effect. Dozens of other telescopes, from small amateur instruments to professional observatories, contributed observations, tracked the object's position, measured its brightness, monitored its activity. This was not just a scientific effort, it was a global collaboration involving astronomers from dozens of countries, working together across time zones, sharing data in real time, coordinating observations to maximize the scientific return. The Minor Planet Center served as the central repository for astrometric observations, the precise measurements of the object's position that allowed astronomers to calculate its orbit. The International Astronomical Union's Small Body Node coordinated the follow-up campaign, ensuring that telescopes around the world were observing at the right times with the right instruments. The urgency was real. Interstellar objects move fast. They pass through the inner solar system quickly, and once they move beyond the orbit of Jupiter, they become too faint to study in detail. The window for observation was narrow, perhaps a few months at most. Every night counted. Every observation was precious. And the astronomical community knew that if they missed something, if they failed to observe at the right time, the information would be lost forever. Larry Deno and John Tonry, the Atlas team members who had been on Mauna Loa when the discovery was confirmed, immediately began coordinating follow-up observations with their network of telescopes. Atlas had 5 sites around the world, 2 in Sekionsatiri, Hawaii, 1 in Chile, 1 in South Africa, and 1 planned for the Northern Hemisphere. This global coverage allowed them to monitor the object continuously, to track its brightness changes, to detect any outbursts or unusual activity. "We knew this was special from the moment we realized it was interstellar," Deno said. "But we had no idea just how special it would turn out to be. Every new observation brought a new surprise, a new mystery, a new question." The amateur astronomy community also played a crucial role. Amateur astronomers around the world contributed observations, tracked the object's position, measured its brightness, captured images that revealed the structure of the coma and tail. In an era when professional astronomy was increasingly dominated by large, expensive facilities, the contribution of amateur astronomers was a reminder that discovery was still possible for anyone with a telescope, a camera, and the dedication to observe. Social media became a vital tool for coordination and communication. Astronomers shared observations in real time, discussed interpretations, debated theories. The hashtag #3IATLAS trended on Twitter as news of the discovery spread beyond the astronomical community to the general public. People around the world followed the object's journey, eager to learn about this visitor from another star system. The observation campaign was not without challenges. 3I/Atlas was faint, requiring large telescopes and long exposure times to obtain useful data. It was moving rapidly across the sky, requiring telescopes to track at non-sidereal rates, to follow the object's motion rather than the fixed stars. And it was active, releasing gas and dust that created a coma and tail, complicating the measurements of its nucleus and its intrinsic brightness. Weather was always a concern. Clouds could ruin a night of observations, and with the object moving quickly, lost time could not be recovered. Telescope scheduling was competitive, with dozens of proposals submitted for time on the world's largest facilities. The astronomers studying 3I/Atlas had to justify their observations, to demonstrate the scientific importance, to convince telescope allocation committees that this object deserved priority over other targets. But despite these challenges, the campaign was a triumph. The data poured in, terabytes of observations, spectra, images, measurements. Astronomers worked around the clock to analyze the data, to extract the scientific results, to publish the findings. Papers were submitted to journals at an unprecedented rate, each one revealing a new aspect of this remarkable object. The methanol abundance was published first, the ALMA observations showing the extraordinary ratio of CH3OH to HCN. Then came the James Webb results, the detection of carbon dioxide, and the measurement of the CO2/H2O ratio. The Very Large Telescope spectrum revealed the nickel without iron, the chemical impossibility that drove theorists to propose new formation mechanisms. The Tianma observations showed the extended water source, the icy grains sublimating in the coma. Each discovery built on the others, creating a coherent picture of an object that was fundamentally different from anything in our solar system. The global observation campaign had succeeded. In just a few months, astronomers had learned more about an interstellar object than they had about Oumuamua and Borisov combined. They had obtained spectra, measured composition, tracked activity, determined size, calculated age. They had turned a faint point of light into a world, a visitor from another star system into a scientific treasure trove. But the campaign was not just about science. It was about inspiration, about showing the public that discovery was still possible, that the universe still held surprises, that we were living in a golden age of astronomy. The story of 3I/Atlas captured the imagination of people around the world, reminding them that we are part of a vast cosmos, that we are not alone in the universe, that there are objects passing through our solar system from other stars, carrying the secrets of distant worlds. Schools used the object as a teaching tool, showing students how to track it in the sky, how to understand its orbit, how to appreciate its significance. Museums created exhibits about interstellar objects, explaining the science, showcasing the images, celebrating the discovery. Documentaries were filmed, articles were written, podcasts were recorded. The story of 3I/Atlas became a cultural phenomenon, a reminder of the power of human curiosity, of our drive to explore, to understand, to push beyond the boundaries of knowledge. And through it all, the object continued on its journey, moving away from the sun, fading from view, preparing to leave our solar system forever. The observation campaign was winding down, the telescopes turning to other targets, the astronomers publishing their final results. But the legacy of the campaign would endure. The data would be analyzed for years, the theories debated, the implications explored. 3I/Atlas had given us a gift, a window into the ancient galaxy, a glimpse of the diversity of the cosmos. And we had accepted that gift, had studied it, had learned from it. The global observation campaign was over, but the story of 3I/Atlas was just beginning. Chapter 6: The Mysteries That Remain. For all we learned about 3I/Atlas, for all the data we collected, for all the theories we developed, mysteries remained. Questions that we could not answer, puzzles that we could not solve. Because 3I/Atlas was not just an object to be studied, analyzed, categorized. It was a reminder of how much we do not know, of how much there is to discover, of how vast and strange and wonderful the universe truly is. The nickel without iron remained the most baffling mystery. Despite extensive searches, despite observations with the most sensitive instruments, no iron was detected in the coma. The nickel tetracarbonyl hypothesis was plausible, but it raised more questions than it answered. Why had nickel formed volatile compounds while iron had not? What conditions in the protoplanetary disk had allowed this chemical fractionation? Was this a common feature of interstellar objects, or was 3I/Atlas unique? Laboratory experiments were proposed to test the nickel tetracarbonyl hypothesis. Could such molecules form under the conditions expected in protoplanetary disks? Could they survive the journey through interstellar space? Could they sublimate at the distances from the Sun where 3I/Atlas was active? Theoretical models were developed, simulations run, calculations performed, but the answer remained elusive. The nickel without iron was a chemical impossibility that demanded explanation, and we did not yet have that explanation. The extended water source was another puzzle. The observation that up to 80% of the water, vapor was coming from icy grains in the coma rather than directly from the nucleus was unprecedented. Only one solar system comet, 103P/Hartley, had shown a similar effect, and even there, it was not the dominant mechanism. What made 3I/Atlas so different? Why was it releasing such large, icy grains? What did this tell us about the structure and composition of the nucleus? Models were developed to explain the extended source. Perhaps the nucleus was a rubble pile, a loose aggregation of icy chunks held together by gravity that was shedding material as it rotated. Perhaps the surface was covered in a layer of refractory material that insulated the interior ice, causing pressure to build up until it exploded, ejecting large chunks into the coma. Perhaps the object was undergoing a process of fragmentation, breaking apart as it approached the Sun. But these were just hypotheses. Without a close-up view of the nucleus, without a spacecraft to fly by and take images, we could not know for certain. The extended water source remained a mystery, a clue to the object's internal structure that we could not fully interpret. The age calculation was another source of uncertainty. 7 billion years was the best estimate, based on the object's velocity and trajectory. But this calculation depended on models of galactic dynamics, on assumptions about the object's origin, on our understanding of how objects move through the galaxy over billions of years. What if those models were wrong? What if the object had been accelerated by interactions we did not understand? What if it was younger or older than we thought? The uncertainty was frustrating. The age was one of the most profound aspects of 3I/Atlas, the fact that it was the oldest macroscopic object we had ever observed. But if we could not be certain of that age, if the calculation was based on assumptions that might be wrong, then the significance was diminished. Astronomers continued to refine the models, to improve the calculations, to search for independent ways to estimate the age. But the uncertainty remained. The formation environment was another mystery. The chemistry of 3I/Atlas suggested formation in a very cold region of a protoplanetary disk, far beyond the ice giants, possibly beyond the CO snowline. But how cold? How far? What was the nature of the parent star? Was it a sun-like star, or something different? What was the composition of the disk? How did the conditions there differ from our solar system? These questions could not be answered by observations of 3I/Atlas alone. We needed to understand the diversity of protoplanetary disks, the range of conditions where planets and comets can form. We needed to study young stellar systems, to observe disks around other stars, to develop models of disk chemistry and evolution. This was ongoing work, a field of astronomy that was rapidly advancing, but it would take time to connect the observations of 3I/Atlas to a specific formation scenario. The ejection mechanism was also uncertain. How had 3I/Atlas been flung out of its home system? Was it ejected by a giant planet, scattered outward by gravitational interactions during the chaotic early stages of planetary formation? Was it the result of a stellar encounter, a close passage of another star that disrupted the system and sent objects flying into interstellar space? Was it the product of the star's death, ejected when the star became a red giant and engulfed the inner planets? Each mechanism had different implications for the object's history, for the timing of the ejection, for the nature of the parent system. But without more information, we could not distinguish between them. The ejection mechanism remained a mystery, a gap in our understanding of how interstellar objects are produced. And then there was the question of representativeness. Was 3I/Atlas typical of interstellar objects? Or was it unusual, a rare example of a particular type? We had only seen 3 interstellar objects. 3 was not enough to establish a population, to determine the diversity, to understand the range of possibilities. Was 3I/Atlas the norm or the exception? This question could only be answered by finding more interstellar objects, by detecting dozens, hundreds, thousands of them, and studying their properties, their compositions, their orbits. This was the goal of upcoming surveys, of next-generation telescopes, of the continuing search for objects from other star systems. But it would take time. For now, 3I/Atlas stood alone, a singular object that challenged our understanding, that defied our expectations, that reminded us of how much we had yet to learn. The mysteries that remained were not failures. They were opportunities. They were the questions that would drive future research, that would inspire new observations, that would lead to new discoveries. Science advances not by answering all the questions, but by asking better questions. And 3I/Atlas had given us better questions to ask. It had shown us that interstellar objects could be chemically diverse, that they could contain molecules in ratios we had never seen, that they could challenge our understanding of planetary formation. It had shown us that they could be ancient, that they could survive for billions of years in interstellar space, that they could carry the chemical fingerprint of the early galaxy. It had shown us that they could be active in unexpected ways, that they could release water from extended sources, that they could surprise us with every new observation. The mysteries that remained were a testament to the object's complexity, to the richness of the information it carried, to the depth of the secrets it held. They were a reminder that discovery is a process, not an endpoint, that understanding is provisional, subject to revision as new data becomes available, that the universe is under no obligation to conform to our expectations, to make sense to us, to reveal its secrets easily. 3I/Atlas had given us a gift, but it had also given us a challenge, the challenge to understand, to explain, to solve the mysteries. And that challenge would keep astronomers busy for years, perhaps decades to come. Because the most surprising object in space was not just surprising for what it revealed. It was surprising for what it concealed, for the questions it raised, for the mysteries it left behind. And those mysteries were the most valuable gift of all. Chapter 7: The Implications for Planetary Formation. The discovery of 3I/Atlas did more than just add another object to the catalog of interstellar visitors. It fundamentally challenged our understanding of how planetary systems form, how comets and asteroids are created, how the building blocks of planets are assembled. The object's chemistry, its age, its size, its activity, all of these properties told a story of formation under conditions vastly different from those in our solar system. And that story forced us to reconsider our models of planetary formation, to expand our understanding of the diversity of planetary systems, to acknowledge that our solar system is just one example among many. The methanol abundance was perhaps the most striking clue. The ratio of methanol to hydrogen cyanide in 3I/ Atlas was an order of magnitude higher than in any solar system comet. This suggested formation in an environment that was extraordinarily cold, where the chemistry was dominated by hydrogenation reactions, where carbon monoxide was efficiently converted to methanol on the surfaces of dust grains. Such conditions would exist only in the outermost reaches of a protoplanetary disk, far beyond where the ice giants form in our solar system, possibly beyond 50 or even 100 astronomical units from the parent star. But our models of protoplanetary disks suggested that the density of material at such distances would be very low. There would not be enough solid material to form kilometer-scale objects like 3I/Atlas. The timescales for growth by accretion would be too long, longer than the lifetime of the disk. So how could such a large object form so far from the star? One possibility was radial mixing. Perhaps 3I/Atlas had formed closer to the star, where the density was higher, and then been transported outward by interactions with the gas disk or with forming planets. But this would have exposed the object to warmer temperatures, which would have altered its chemistry, would have prevented the extreme methanol enrichment. So radial mixing seemed unlikely. Another possibility was that the protoplanetary disk of 3I/Atlas's parent star was different from the disks we observe around young stars in our galaxy. Perhaps it was more massive, with more solid material at large distances. Perhaps it was colder, allowing ices to condense closer to the star. Perhaps it had a different chemical composition, with more carbon relative to oxygen, which would favor the formation of methanol over other molecules. These possibilities suggested that protoplanetary disks are more diverse than we had thought, that they can have different masses, different temperatures, different chemical compositions, different structures, that the conditions where planets and comets form can vary widely from system to system, and that our solar system, with its particular configuration of planets and comets, is just one example among many. The carbon dioxide abundance provided another clue. The high CO2/H2O ratio suggested either formation at extreme distances from the star, where CO2 could condense but water remained in vapor form, or extensive processing by cosmic rays during billions of years in interstellar space. If the former, it reinforced the picture of formation in the outermost regions of the disk. If the latter, it suggested that interstellar objects can be significantly modified by their journey through the galaxy, that their surface composition may not reflect their original formation conditions. The nickel without iron was perhaps the most challenging puzzle for planetary formation models. Nickel and iron are typically found together, produced in the same stellar processes, condensed into the same types of grains. To find one without the other suggested a chemical fractionation process that we did not understand. Perhaps the nickel had been incorporated into volatile molecules, like nickel tetracarbonyl, while the iron remained locked in refractory grains. But why would this happen? what conditions would favor such fractionation. One possibility was that the parent star had an unusual composition, with more nickel relative to iron than typical stars. But this seemed unlikely, as nickel and iron are produced together in supernovae, and their ratio is relatively constant in the galaxy. Another possibility was that the temperature and pressure conditions in the disk had allowed nickel to form volatile compounds, while iron had not. But this would require very specific conditions that we had not considered in our models. The mystery of the nickel without iron highlighted a fundamental limitation in our understanding of planetary formation. We had developed models based on the objects in our solar system, on the meteorites we had studied, on the comets we had observed. But these models assumed a certain range of conditions, a certain chemical composition, a certain set of physical processes. 3I/Atlas was showing us that reality could be different, that there were conditions we had not considered, processes we had not imagined, chemistries we had not expected. The size of 3I/Atlas was another challenge. At up to 20 kilometers in diameter, it was an order of magnitude larger than the previous interstellar objects. This suggested that large objects could be ejected from planetary systems, that they could survive the ejection process, that they could travel through interstellar space for billions of years without being destroyed. But our models of planetary formation suggested that large objects should be rare in the outer regions of disks, where the density of material was low. So how had 3I/Atlas grown to such a size? One possibility was that it had formed by the gravitational collapse of a cloud of pebbles, a process known as streaming instability. In this scenario, solid particles in the disk concentrate into dense clumps that collapse under their own gravity, forming large objects directly, without the need for gradual growth by accretion. This process could operate at large distances from the star, where the orbital timescales were long and gradual growth was inefficient. But it required specific conditions: a high concentration of solid particles, low turbulence in the disk, and it was not clear if these conditions would be met in the outer regions of disks. Another possibility was that 3I/Atlas had formed closer to the star, where the density was higher, and then been scattered outward before being ejected from the system. But this would have exposed it to warmer temperatures, which would have altered its chemistry. So this scenario also seemed unlikely. The size mystery highlighted another limitation in our models. We had assumed that interstellar objects would be small, that only small objects could be ejected from planetary systems, that large objects would remain bound to their stars. 3I/Atlas was showing us that this assumption was wrong, that large objects could be ejected, that the population of interstellar objects could include a wide range of sizes. The age of 3I/Atlas had implications for the history of planetary formation in the galaxy. If the object was truly 7 billion years old, it had formed when the galaxy was young, when the metallicity was lower, when the conditions for planet formation were different. And yet, it contained complex organic molecules, prebiotic chemistry, the building blocks of life. This suggested that the chemistry of life's origins was not limited to a narrow window of time, to stars with solar metallicity, to specific types of planetary systems. It was universal, a natural consequence of the chemistry of the cosmos, available wherever and whenever planets formed. This had profound implications for the search for life elsewhere in the universe. If prebiotic molecules could form in the protoplanetary disks of ancient metal-poor stars, then the ingredients for life were not rare. They were common, ubiquitous, a natural product of planetary formation. This increased the likelihood that life could arise on planets around a wide range of stars, in a wide range of environments, at a wide range of times in the galaxy's history. The implications of 3I/Atlas for planetary formation were far-reaching. It had shown us that protoplanetary disks are more diverse than we had thought, that the conditions where planets and comets form can vary widely, that large objects can form in the outer regions of disks. That chemical fractionation can produce compositions we had not expected. That prebiotic chemistry is universal, that interstellar objects can survive for billions of years. It had forced us to expand our models, to consider new processes, to acknowledge the limits of our understanding. It had reminded us that our solar system is just one example among many, that the diversity of planetary systems is vast, that there are surprises waiting to be discovered. And it had given us a new perspective on our place in the cosmos. We were not living in a typical planetary system, orbiting a typical star, surrounded by typical objects. We were living in one specific example of the vast diversity of the galaxy. And by studying objects like 3I/Atlas, by learning about the conditions in other planetary systems, we were beginning to understand that diversity, to appreciate the range of possibilities, to grasp the true nature of the cosmos we inhabit. The implications for planetary formation were just beginning to be explored. There would be more discoveries, more surprises, more challenges to our understanding. But 3I/Atlas had opened the door. It had shown us the way. And we would follow, driven by curiosity, by the desire to understand, by the knowledge that the universe still held secrets waiting to be discovered. Chapter 8: The Future of Interstellar Exploration. The discovery of 3I/Atlas was not an endpoint. It was a beginning. A new chapter in our exploration of the cosmos, in our understanding of planetary systems, in our search for the origins of life. The object had shown us that interstellar visitors are more common, more diverse, more surprising than we had imagined. And it had given us a glimpse of what future discoveries might reveal. The next decade would see a revolution in our ability to detect and study interstellar objects. New surveys were being planned, new telescopes were being built, new techniques were being developed. The Vera C. Rubin Observatory, under construction in Chile, would begin operations in the coming years, scanning the entire southern sky every few nights, detecting faint moving objects with unprecedented sensitivity. It was expected to discover dozens of interstellar objects, perhaps even hundreds, providing a statistical sample that would allow us to understand the population, the diversity, the origins of these visitors from other star systems. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, would conduct a microlensing survey that could detect interstellar objects too small or too distant to be seen by other means. By measuring the gravitational lensing effect of these objects on background stars, it could reveal a hidden population of interstellar wanderers, objects that would otherwise remain invisible. Next-generation spectrographs on large telescopes would allow us to obtain detailed chemical compositions of interstellar objects to detect molecules that were currently beyond our reach, to compare the chemistries of objects from different star systems. We would begin to build a database of interstellar compositions, a catalog of the chemical diversity of the galaxy, a window into the conditions where planets form around different types of stars. But the most ambitious plans involved sending spacecraft to intercept interstellar objects. The European Space Agency was studying the Comet Interceptor mission designed to visit a long-period comet or an interstellar object. The spacecraft would wait at the L2 Lagrange point, and when a suitable target was discovered, it would launch, racing to intercept the object before it left the inner solar system. It would deploy multiple probes, obtaining images, spectra, and in situ measurements of the coma and nucleus. NASA was also studying concepts for interstellar object missions. The idea was challenging. Interstellar objects moved fast, and they were discovered late, often when they were already leaving the inner solar system. Reaching them would require rapid response, powerful rockets, and precise navigation. But the scientific payoff would be enormous. A close-up view of an interstellar object, detailed images of its surface, direct measurements of its composition, would revolutionize our understanding of these visitors from other star systems. Some proposals were even more ambitious. Concepts for missions that would rendezvous with interstellar objects, that would match their velocity and travel alongside them for extended periods, that would study them as they moved through the solar system. Such missions would require advanced propulsion systems, perhaps solar sails or ion drives, but they would provide unprecedented opportunities for scientific study. Beyond missions to specific objects, there were plans for more general interstellar exploration. The Breakthrough Starshot initiative was studying concepts for sending tiny spacecraft to nearby star systems, propelled by powerful lasers, reaching speeds of a significant fraction of the speed of light. Such missions would take decades to develop, but they would allow us to explore other planetary systems directly, to visit the birthplaces of interstellar objects, to understand the environments from which they came. The study of interstellar objects was also driving advances in technology. The need to detect faint, fast-moving objects was pushing the limits of telescope design, of detector sensitivity, of data processing. The need to rapidly characterize new discoveries was driving advances in spectroscopy, in remote sensing, in automated analysis. The need to plan missions on short timescales was driving advances in spacecraft design, in propulsion, in navigation. These advances would benefit all of astronomy, not just the study of interstellar objects. Better telescopes would reveal fainter galaxies, more distant quasars, older stars. Better detectors would detect exoplanets, measure their atmospheres, search for signs of life. Better data processing would handle the deluge of information from modern surveys, would find patterns in the data, would make new discoveries. But perhaps the most important advance was in our understanding. The discovery of 3I/Atlas had shown us that the galaxy was a dynamic place, where material was constantly being exchanged between star systems, that our solar system was not isolated, but part of a larger community of planetary systems, connected by the flow of interstellar objects. that the building blocks of planets, of comets, of life itself could travel between the stars, carrying the chemical fingerprints of their birthplaces, seeding the galaxy with the ingredients for worlds and life. This understanding was changing our perspective on our place in the cosmos. We were not alone in the universe, not just in the sense that there might be life on other planets, but in the more fundamental sense that we were connected to other star systems, that material from those systems was passing through our neighborhood, that we could study those systems by analyzing the objects they had ejected. The future of interstellar exploration was bright. There would be more discoveries, more surprises, more challenges to our understanding. We would find objects larger than 3I/Atlas, smaller, older, younger, with different chemistries, different activities, different origins. We would build a statistical sample that would allow us to understand the population, to trace the history of planetary formation in the galaxy, to search for patterns in the diversity. And perhaps one day, we would send a spacecraft to intercept an interstellar object. We would obtain close-up images of its surface, direct measurements of its composition, in situ analysis of its activity. We would learn things that we could not learn from remote observations, things that would revolutionize our understanding of these visitors from other star systems. The future was uncertain. There would be setbacks, failures, disappointments. Not every mission would succeed. Not every discovery would be as surprising as 3I/Atlas. But the journey would continue, driven by curiosity, by the desire to understand, by the knowledge that the universe still held secrets waiting to be discovered. 3I/Atlas had shown us the way. It had opened our eyes to the diversity of the cosmos, to the reality of interstellar exchange, to the possibility of surprises, and we would follow, exploring the galaxy one interstellar object at a time, learning the stories they carried, understanding the worlds they came from, appreciating the vast and wonderful universe we inhabit. The future of interstellar exploration was just beginning, and it would be a future full of surprises. Chapter 9. The Final Farewell. There is a specific moment when an interstellar object ceases to be a presence and becomes a memory. It is not a dramatic event. There is no explosion, no final flash of light, no signal sent back to Earth. It is simply a fading, a gradual dimming until the signal-to-noise ratio drops below 1, until the object is indistinguishable from the background static of the universe. For 3I/Atlas, that moment was approaching. As it swung around the sun, using the star's gravity to slingshot itself back into the interstellar void, it began to recede. The distance grew. The light weakened. The window of opportunity was closing. For the astronomers who had spent months tracking this ancient traveler, the departure was bittersweet. There was relief, certainly. The data had been collected, the spectra had been taken, the mysteries had been catalogued, even if they had not all been solved. But there was also a profound sense of loss. This object had been a companion of sorts. It had been a tangible connection to the wider galaxy, a physical proof that we are not isolated. And now, it was leaving. It was returning to the darkness from whence it came, carrying with it the record of its brief encounter with our solar system. The trajectory was precise. Hyperbolic excess velocity of approximately 60 kilometers per second. This was the speed at which it would travel forever, unless it encountered another star system, another gravitational well, another chance encounter in the vast emptiness between the stars. It was moving too fast to be captured. The sun had tried to hold it, had bent its path, had heated its ices, had drawn out its secrets. But the gravity was not enough. The object was bound to the galaxy, not to any single star. It belonged to the void. As the object moved beyond the orbit of Jupiter, the observations became more difficult. The apparent magnitude dropped. The coma expanded and thinned. The tail stretched out across millions of kilometers, becoming fainter, more diffuse. Telescopes that had once tracked it easily now had to integrate for hours to capture enough photons for a meaningful spectrum. The global campaign was winding down. The large facilities were needed for other targets. The urgency was fading, replaced by the slow, methodical work of data analysis. But a dedicated group of astronomers kept watching. They knew that the final data points were crucial. The behavior of the object at large distances from the sun could reveal information about its internal structure, about the depth of its volatile ices, about the thickness of its radiation mantle. As the sunlight weakened, the sublimation rate should have dropped. But did it? Or did the object remain active further out than expected? This was a key question. If 3I/Atlas remained active at 5 astronomical units, at 10, at 15, it suggested that the volatile ices were not just on the surface, but deep within the nucleus. It suggested that the object was pristine, that the billions of years in interstellar space had not completely devolatilized it. The last successful spectroscopic observation was made in late October. The Very Large Telescope in Chile pointed its mirrors at the faint smudge of light one last time. The exposure lasted for 4 hours. The data was noisy, filled with cosmic rays, with atmospheric interference, with the inherent uncertainty of observing a moving target at the limit of detectability. But there was signal. There was still water. There was still carbon monoxide. The object was still outgassing, still releasing the ancient ices that had been preserved since the dawn of the galaxy. Then the weather turned. Clouds rolled over the Andes. The telescope had to close. When the skies cleared a week later, the object was too faint. The signal was lost. It was gone. Not physically, of course. It was still there, tumbling through the darkness, continuing its journey. But for us, it was gone. It had crossed the threshold of observability. It had become invisible. This moment of loss is unique to astronomy. In most fields of science, the object of study remains. A biologist can return to the forest. A geologist can return to the rock face. A chemist can return to the lab bench. But an astronomer cannot return to the moment. When the light fades, it is gone forever. The object moves on. The opportunity is lost. This impermanence adds a layer of poignancy to the work. Every observation is precious. Every photon counts. Because you know, with absolute certainty, that you will never see this object again. For 3I/Atlas, the farewell was final. It would not return in 1,000 years, or 1,000,000, or 1,000,000,000. It was on a one-way trip through the galaxy. It might pass through another solar system in a few million years. It might be discovered by another civilization, around another star, by beings who might wonder about its origin, who might analyze its chemistry, who might see the scars of its passage through our system. But that was speculative. That was science fiction. The reality was that it was leaving us, and we were staying here. The data, however, remained. Terabytes of images, spectra, light curves, astrometric measurements. This was the legacy of the encounter. This was what remained when the light faded. The data would be archived, stored in repositories accessible to astronomers around the world. It would be analyzed for years, perhaps decades. New techniques would be developed, new algorithms written, and the old data would be re-examined. Secrets hidden in the noise might be revealed. Patterns might be found that were not visible in the rush of the initial discovery. This is the nature of modern astronomy. The observation is temporary, but the data is permanent. The object leaves, but the information stays. We build monuments not of stone or steel, but of bits and bytes. We preserve the light that has already faded. We keep the memory of the visitor alive in the archives. And in doing so, we ensure that the discovery continues to yield insights long after the object itself is unreachable. The departure of 3I/Atlas also marked a transition in the field of interstellar studies. Before Oumuamua, the idea of interstellar objects was theoretical. Before Borisov, it was uncertain. Before 3I/Atlas, it was rare. But now, with 3 confirmed objects and dozens more expected in the coming decade, the field was maturing. We were moving from the era of discovery to the era of characterization. We were no longer just finding them. We were understanding them. We were building a taxonomy of interstellar objects. We were learning the demographics of the galaxy. This transition was driven by the farewell of 3I/Atlas. It showed us what was possible. It showed us the limits of our current technology. It showed us where we needed to improve. The fact that we lost the object when it did, that we could not track it further, highlighted the need for more sensitive telescopes, for faster response times, for better coordination. It drove the proposals for new surveys, for new missions, for new infrastructure. The departure was not just an end, it was a catalyst. There was also a philosophical weight to the farewell. We had hosted a visitor from another world. We had studied it. We had learned from it. And then we had let it go. It was a reminder of our place in the cosmos. We are stationary, bound to our star, confined to our solar system. The objects of the galaxy are free. They move between the stars. They traverse the void. They are the true citizens of the Milky Way. We are the locals. They are the travelers. And for a brief moment, one of them stopped in our driveway. This perspective shift is profound. It changes how we view the sky. It is no longer just a collection of fixed stars and distant galaxies. It is a dynamic environment. It is a place where things move, where objects pass through, where the inventory is constantly changing. The sky is alive, and 3I/Atlas was proof of that life. It was a moving piece of the cosmic puzzle, a fragment of another world that had briefly become part of ours. As the object faded, the astronomers who had studied it began to write the papers. They compiled the results, the graphs, the models. They debated the interpretations, the uncertainties, the implications. They prepared to share the knowledge with the world. This was the final act of the encounter, the translation of light into knowledge, the conversion of photons into understanding. It was an alchemy of sorts, taking the faint glow of a distant object and turning it into insight about the nature of reality. The final paper was submitted to the Astrophysical Journal. The title was technical, dry, precise, but the content was extraordinary. It detailed the chemistry, the orbit, the age, the mysteries. It was the official record of the encounter. It was the tombstone of the observation, but also the birth certificate of the knowledge. Once published, the information belonged to everyone. It was part of the collective understanding of humanity. It was a permanent addition to the library of science. But for the astronomers who had lived through the discovery, the feeling was personal. They remembered the night of the alert, the rush to the telescope, the cold air of the observatory, the glow of the computer screens, the moment of realization, the excitement of the unexpected. These memories were as much a part of the discovery as the data. They were the human context of the science. And as the object faded, those memories became the primary connection to the visitor. The data was abstract. The memory was real. The farewell was complete. 3I/Atlas was gone. The telescopes had turned to other targets. The sky had returned to its usual state. But everything had changed. We knew now that such objects existed. We knew what they could look like. We knew what they could teach us. We knew that the galaxy was full of them. And we knew that we were ready for the next one. Because there would be a next one. And the one after that. And the one after that. The era of interstellar astronomy had begun. And 3I/Atlas was the object that defined it. It was the standard against which all future discoveries would be measured. It was the benchmark. It was the surprise that started it all. As the object traveled onward into the darkness, it carried with it a tiny piece of us. Not physically, but in the data, in the knowledge, in the understanding. We had touched it with our light. We had analyzed its atmosphere. We had measured its speed. We had known it, and in knowing it, we had connected with it. A connection across the void. A connection across time. A connection across the galaxy. The farewell was not an end. It was a bridge. A bridge between our solar system and the rest of the galaxy. A bridge between the present and the ancient past. A bridge between what we knew and what we had yet to discover. And as the object crossed that bridge, disappearing into the night, it left the door open. It left the invitation. It left the promise that there was more to see. So we watched it go. We recorded the final coordinates. We logged the last magnitude. We closed the telescope dome. And we waited. Because the sky was still there. The stars were still shining. The darkness was still full of secrets. And the next visitor was already on its way. The farewell was over. The legacy had begun. Conclusion. The most surprising object in space was not surprising because it was large or old or chemically unusual. It was surprising because it challenged everything we thought we knew. It violated our expectations, broke our models, forced us to confront the limits of our understanding. It reminded us that the universe is under no obligation to conform to our theories, to make sense to us, to reveal its secrets easily. 3I/Atlas was a messenger from the ancient galaxy, a traveler that had crossed the void between the stars for 7 billion years to reach us. It carried the chemical fingerprint of a world that may no longer exist, of a star that may have died eons ago, of a planetary system that was young when our galaxy was young. It told us a story of formation in conditions we could barely imagine, of ejection by forces we could not see, of survival in an environment that should have destroyed it. And in telling that story, it taught us profound lessons. It taught us that our solar system is not typical, that the diversity of planetary systems is vast, that there are worlds out there formed under conditions we cannot replicate. It taught us that the chemistry of life's building blocks is universal, that prebiotic molecules can form in a wide range of environments, that the ingredients for life are common in the cosmos. It taught us that the galaxy is a dynamic place where material is constantly being exchanged between star systems, where we are connected to distant worlds by the flow of interstellar objects. But perhaps most importantly, it taught us humility. It reminded us that we are just beginning to explore the cosmos, that our knowledge is provisional, subject to revision as new data becomes available, that there are surprises waiting in the darkness, that the next discovery could change everything, that the universe is far stranger and more wonderful than we had ever imagined. The story of 3I/Atlas was not just a story about a comet. It was a story about discovery, about the moment when the universe reveals something so unexpected, so impossible, that it forces us to rewrite our understanding of reality. It was a story about the fragility of human knowledge, about how quickly certainty can crumble in the face of new evidence. It was a story about the relentless curiosity that drives us to look up, to search, to question, to push beyond the boundaries of what we think we know. And it was a story that was not over. The object would continue on its journey, leaving our solar system, disappearing into the darkness, never to return. But the data we had collected, the lessons we had learned, the questions we had raised would endure. They would drive future research, inspire new observations, lead to new discoveries. The story of 3I/Atlas would be told and retold in scientific papers, in documentaries, in classrooms, in the minds of anyone who looked up at the night sky and wondered what else was out there. Because that is the true legacy of the most surprising object in space. It was not just what it taught us about comets, or planetary formation, or interstellar chemistry. It was what it taught us about ourselves, about our capacity for wonder, for curiosity, for exploration, about our drive to understand the cosmos, to know our place in it, to push beyond the boundaries of the known. 3I/Atlas had delivered its message, and we had listened, we had learned, we had grown, and we would continue to learn, to grow, to explore, driven by the knowledge that the universe still held surprises, that there were more stories to be discovered, more mysteries to be solved, more wonders to be found. The most surprising object in space was not an endpoint. It was a beginning, a new chapter in our exploration of the cosmos. And the story was just beginning.